Hi friends, this is Dr. G. Srinivasa Gupta, Professor from Department of Mechanical Engineering of VJEC Institute of Engineering Technology. As part of Dynamics of Machinery course, today we are going to discuss a numerical exercise on partial balancing of locomotives. In my previous discussion, just we have seen what are types of locomotives, coupled, uncoupled. Coupled locomotive means two or more pairs of wheels coupled together to increase adhesive force between the wheels and track, as you know. Otherwise, it is called uncoupled. And locomotives have two cylinders generally. These locomotives basically, generally, they have two cylinders. So, inside cylinder locomotive, the cylinders are kept between wheels. This is inside cylinder locomotive. Outside means outside the wheels. Wheels are in between the cylinders. So, this is outside cylinder locomotive. So, the cranks of two cylinders generally kept at 90 degrees. Okay, this is the thing we have seen yesterday. Okay, coupled locomotive connect the crank pins with coupling rods. As coupling rods revolve with the crank pin, so complete balancing is possible. So, we have seen that. And effect of partial balancing in locomotives, full balance we cannot do, as you know that. We have seen also the effect of full balancing if you are going to do by attaching the mass opposite to the crank with some radius, then there will be a effect hammer blow. That is most disadvantage and effect on the engine performance. So, we are compromising and we are going to partially balance the unbalanced masses. That is inertia forces which are due to reciprocating masses. This is piston in this case. So, so the effect of partial balancing is hammer blow, variation of tractive effect, swaying couple. All these we have studied, just thoroughly discussed in previous lecture. So, this let me remind the variation of tractive effect is plus or minus square root of 1 minus c m r omega square. This is maximum variation. Similarly, swaying couple is plus or minus 1 by root 2 into 1 minus c m r omega square into L, length between the cylinder center lines. Okay, the hammer blow, you know that mass balanced mb or omega square. That is hammer blow. We can magnitude wise we can calculate. Now we are taking some example problem on this locomotive engines. Okay, so and also we have discussed secondary balancing regarding crank secondary balancing also in the last class. Okay, today we are going to deal with a numerical exercise on this unbalancing part of the locomotives. This is the problem. Let us see the following data refer to two-cylinder uncoupled locomotive. So, rotating masses per cylinder. Generally, this is cylinders are kept at the wheels are kept at the outside the cylinders. So let me draw a line. This is the cylinders. Okay, two cylinders and wheels. These lines, center lines of these representing. Let us say 2 and 3 are cylinders, 1 and 4 are wheels. Okay, so this is 4 planes because it is uncoupled. Uncoupled always there are 4 planes in case of locomotives, 2-cylinder engine. So rotating mass per cylinder is 280 kg given. Reciprocating mass per cylinder is 300 kg given. So rotating mass balance we can do completely, but reciprocating mass is only the problem to make it balance. So distance between the wheels is given for 1400. Distance between the wheels, this distance is 1400. Okay, this is 1400 mm. Okay, wheels 1 and 4 are wheels, and distance between the cylinder centers is 600. So this is the 600 given. Obviously you will have 600, then this distance is 400 and 400 here, you know that. So cylinder 3 and wheel 4 and cylinder 2 and wheel 1, the distance is 400 because total 1400. This is underline distance between the cylinders is 600. So okay, so then diameter of treads of driving wheels. So driving wheel diameter is 1800 mm and crank radius in cylinder engine crank radius is R is 300 mm given. Radius of center of balance mass 620 mm. So the balance mass opposite to the crank along the radial direction which is attached at the radius of 620 mm balancing mass, whatever mass we are going to attach to balance it partially. So locomotive speed is given 50 km per hour, angle between cylinder cranks 90 degrees. Suppose this is the cylinder crank orientation is 0 degrees theta, okay, theta is 0, this is theta is 90. Okay, this is because this view is isometric view, so it is 90 degrees angle between this and this. Okay, then dead load on each wheel. Actually, dead load means the load which is coming on the rail because of this entire vehicle is 3.5 tons. So now what we need to do is we need to estimate balancing mass required in the planes of driving wheels. So planes of driving wheels, these are the planes of driving wheels. Balancing mass how much required? Okay, in the planes of driving wheels. Let us take this is M1, M2, here M3, M4. Okay, these are the masses total we are using to balance it. Then so the crank angles, this is let us take theta 1, whatever angle of the crank, this wheels, and this is theta 4. We don't know, we need to find this theta 1, theta 4. Okay, after estimating we can show the direction, right? Okay, this theta 2, let us say this is theta 2 and this is theta 3. You know that theta 2 is 0, theta 3 is 90, let us say. Then if you write balancing of couple equation by taking our reference plane is 1, then you can write M2 this couple equation, balancing of all couple due to all these okay forces due to masses attached, okay, M2 R2, okay, omega square. Okay, omega we are not writing, common to all because the entire shaft is rotating with same speed. So M2 R2 sine cos, okay, all the components MR cos theta should be balanced. Forces if you consider, and mass you consider into length you need to write. Okay, and MR algebraic sum of MR sin theta must be sin theta into L if you talk about couple. Then M2 R2 L2 cos theta 2 plus M3 R3 L3 cos theta 3 plus M4 R4 L4 cos theta 4 must be equal to 0. This is 1. Okay, algebraic sum must be equal to 0, then it is in balancing. So we are taking this, what is L1, L2, L3, the distance from the reference plane to cylinder on L2, let us say this is L3, okay, L3, and this is L4 is 1400 as you have seen. So if you substitute, then here what is unknown here, okay, theta 4 is unknown in this case, theta 2 is 0, theta 3 is 90. So L2 is, what is L2? 400, L3 is 400 plus 600, 1000. Okay, L3 is, okay, you know the L2 is 400, L3 is 1000, L4 is 1400. Okay, if you substitute, and finally you are arriving with the equation where that is unknown theta, so M4 cos theta 4, you will get some value because R4 you know, L4 you know. So this is radius of wheels and these are given, you substitute those directly. Okay, because you have seen distance diameter of threads of the driving wheels is given, that is 1800 mm. So diameter 1800 by 2 is your wheels radius. Okay, similarly crank radius is given. Okay, so you can substitute and finally you are going to arrive with M4 cos theta 4. Similar equation if you write MR sin theta into L must be equal to 0, then you are going to get M4 sin theta 4. Okay, equal to, okay, some value. You are going to get these values. You can see here. So you are going to get, okay, these m4 cos theta 4 and m4 sin theta 4. You are going to get minus 66.36, m4 cos theta 4, m4 sin theta 4 minus 165.9. One more important thing you need to understand here is total mass to be balanced must be used is MP, means the radial mass attached in the radial direction, that is given here, rotating mass per cylinder 280 and reciprocating mass per cylinder is 300 given, but here in the statement of the problem written is balancing mass required in the planes of driving wheels. Are able to understand if whole of the revolving and 2/3 of the reciprocating mass are to be balanced. So you are able to understand, I think, this driving wheels means M1, M4. So M4 how much you need to use? You should use M4 is 280 is the radial direction rotating mass, 2/3 of reciprocating mass is 300 kg, 2/3 of that 480 kg you have to use M4 on wheels. How much mass you need to keep as balancing mass? Are you able to understand? I think M4 is this one. So balancing mass is this one. So you are going to get, this is balancing mass, not M4. So M4 you are going to get 178.7 kg, okay, and theta 4 is 248.2 degrees. Taking 4 as the reference plane and writing similar equation. You are also going to get, if you write similar equation by taking 4 as the reference plane, means moment about reference plane 4, you take M1 into, okay, L1 distance cos theta 1, M2 L2 distance, M2 R2, M1 R1 cos theta 1 L1, M2 R2 cos theta 2 L2, M3 R3 cos theta 2 cos theta 3 L3. Okay, about 4 you are taking. Okay, those distances you have to take care and write the coupling couple equation, and from that you can see that you will get M1 cos theta 1 is minus 165.9, M1 sin theta 1 is minus 66.36. So if you calculate M1, how do you get M1? Okay, square of both these equations, both sides, and add, then you will get M1 equal to 178.7 kg. So this is same as M4. And theta 1, how do you get? Theta 1 you are going to get, divide this M1 cos theta 1 by M1 sin theta 1. Right side minus 160, okay, you are going to right side minus 165.9 by minus 66.39, that is cot theta 1. So theta 1 you can cot inverse of that you can find. So theta 1 you are going to get 201.8 degrees, and theta 4 while writing M4 equation about reference plane couple equation, you are getting theta 4 is 248.2 degrees. So you can mark these values here. Theta 4 is 248.2. So theta 4 is 248. This is 180 and 68. So this is, okay, crank direction. This is the theta 4 from here. And theta 1 is how much you got? Theta 1 is 201.8. So you can mark this also, 201.8. This is 180 and 201.8 means, okay, 20 small value, this one. Okay, this is theta 1. Are you able to understand? I think. Then once you have M1, M4, then you need to calculate magnitude of M1 could have directly been written equal to M4 you got. Then what is the second question? You need to evaluate swaying couple. Swaying couple, you know that swaying couple is how you are going to get swaying couple. Swaying couple, this is the angular velocity is calculated. You need to, because swaying couple is plus or minus 1 by root 2 into 1 minus c mr omega square L. So omega you need to calculate, because here this vehicle speed is 50 km per hour given. If you convert it into meter per second, then by R, V by R is omega. R is, it is given 1800 wheels, you have seen. This is, what is this 1800? 18 diameter of threads of driving wheels. Okay, so by R. R is radius of wheel, V by R. You write, then you will get omega. Once you have omega, then you can evaluate swaying couple. C is given 2/3 of fractions of the 2/3 portion of the reciprocating masses. That's why C is 2/3. And this equation, swaying couple equation, we have seen yesterday. How do we are going to get it? By taking cylinder crank's position and writing the corresponding unbalanced forces, and the couple arranged due to these forces kept at some distance L. So this equation we are going to use to find the swaying couple. Here we are going to get swaying couple is 3030.3 Newton meter. Variation of tractive effect. This relation also we have seen in the last previous lecture. Then what is that tractive effect relation we derived? Plus or minus square root 2 into 1 minus c m r omega square. Here also substitute, you will get 10,100 newtons is the swaying, variation of tractive force. This is force that is coupled. Next thing asked in the problem is balancing mass for reciprocating parts only. So here you got M1, M4 178.7. So this is combined rotary and rotating and the reciprocating masses together distributed at M1 and M4 you have seen. Then if it is for 480, total you got 480. Okay, 480 is the here. You have calculated total mass to be balanced. That is this one. Okay, 480 kg. But you are going to see that you got M1 and M4 178.7. Corresponding to 178.7 balancing mass, what is the portion of reciprocating masses? So that, but 480 for 480 total mass, balancing mass, then that is reciprocating mass portion is 2/3 of 300. For 178.7 kg mass total, then what is the reciprocating mass portion? That you can obviously write. Okay, 2/3 of 300 by, for 480 it is 2/3 of 300. For 178.7 mass, how much this reciprocating mass portion contributing? So that is, you are going to get 74.46 kg. Okay, so how much balancing mass we are using? 74.46 kg of reciprocating portion. While you evaluating hammer blow, the balancing mass for towards the reciprocating mass balancing only you need to take. This is the MB for hammer blow. Hammer blow mass balanced MB into R omega square. So you can calculate that. The hammer blow 74.46 is the mass is balanced reciprocating portion, and R is 0.62. It is given R is 0.62. You can see here 0.62 R, that is radius of center of balancing mass kept, is 60 mm, so 0.62 meters. Okay, so that is hammer blow you can calculate, and omega you got already 15.43. So this 10,991 newtons is the hammer blow. So and dead load is given. Why dead load is given? Total load is hitting on the rails due to the vehicle. Okay, that is dead load. That is 3.5 tons is given. So if you convert into newtons, 3.5 into 1000 kgs into 9.81. So 335 newtons. So what it is asked in this question is, what is the maximum pressure on rails? You can see it is asked maximum and minimum pressure on rails. So you know that, this is the hammer blow component, which is maximum when theta is 90 and theta is 270. So it is perpendicular line of stroke. One is positive value, other one is negative value. Means direction is towards the rail. That means mass is acting on the rail, this force, that is hammer blow, and other one is lifting the rails. This from the wheels are lifting from the rails. So you can calculate maximum pressure. If you calculate one side, this is dead load plus the hammer blow, because it is downwards on the wheels, rails. Okay, that is 34,335 is the dead load plus 10,991 is the hammer blow on one side, that is to downwards towards the acting on the rails, and other side minimum pressure on rails is 34 335 dead load minus, because it is acting upward, minus it is lifting the wheels. So to keep the wheels on the rail, so this is the force, actually net force acting on the rails. 34 335 minus 10 991, this is the minimum pressure on rails. Okay, maximum is this, minimum is that. Next one is asked is maximum speed of locomotive without lifting the wheels. Here one side lifting the wheels, other side it is just contacting, pressure acting on the wheels maximum. So without lifting means what is the speed of the locomotive you have to determine. For that you need to calculate. Speed means velocity. First you can calculate, because hammer blow without lifting the wheels, hammer blow must be corresponding dead load must be equal to your hammer blow. So maximum speed of locomotive without lifting the wheels from the rails will be when the dead load becomes equal to the hammer blow. So you can take omega is unknown, and you use that hammer blow equal to dead load, then calculate omega, angular velocity of the wheels. Then velocity of the wheels, you know that r omega. So r is given, diameter is given 1800, r omega means r by diameter by 2 into omega, you got 27.27 based on the hammer blow must be equal to dead load on the wheels. Then you got that velocity of the wheels is 88.36 kilometer per hour. If you convert to kilometer per hour, you know that conversion factor. If you get meter per second, that is kilometer per hour, how do you get? 3600 by 1000 if you write, you will get kilometer per hour. So meter per second quantity into 3600 by 1000 will give kilometer per hour. You can verify this value. You are going to get 88.36 kilometer per hour wheels when the wheels should not be lifting from the rail. Means hammer blow must be equal to dead load. Exactly, it will contact always on the wheels. Wheels are contact always on the rails. So this is about the problem. This type of problems one can analyze and solve if locomotives are concerned. In case of 6-cylinder, that is uncoupled the locomotive, this one. Coupled locomotive, if you take, how many planes you have to choose? 6 planes. One is coupling rod plane, other one is wheels plane, and another 2 planes are cylinder planes. 2 cylinder planes, 2 wheels planes, 2 coupling rod planes. 6 planes. The problem procedural solution is similar, but you need to consider here instead of 4 planes, M1, M2, M3, M4, you need to consider here 6 planes. So here you are able to understand, I think total mass to be balanced is we got 480 kg, but while solving this coupling balance equation, we are going to get M1 and M4 values, that is that much only we are going to balance. In that, how much reciprocating part is going to be balanced, we have calculated using the, for 480 reciprocating mass balance, it is 2/3 of 300 kg reciprocating mass, and for 178.7 how much reciprocating mass is balanced. This is used for balancing reciprocating mass. This quantity is useful for evaluating hammer blow. These points are very important to understand. Okay, so in our next lecture we will going to see balancing of inline engines. Okay, we are going to discuss what are inline engines and balancing of them by taking some numerical exercises. With this, I am concluding this lecture here. We will meet again in the next lecture. Thank you.
Like, share, comment, and subscribe VNR Digital Learning Resource YouTube channel.